essentially you have the closed protein shell here that spontaneously forms from free energy minimization processes. And the role of this protein shell for the virus is to protect the viral cargo. So the responsibility of this thing is to protect genome, transcription enzymes, et cetera. And hepatitis B virus, which is pictured here, the leftmost one is the actual crystallographic structure, and then the centermost is the central one is obviously a mathematical simplification of that, where the rhombic subunits are pictured as little polygons, and this hepatitis B virus actually makes the functional form is a larger T equals 4 120 piece structure, which is in the center, and then the smaller one is, you can even see the dodecahedral symmetry, the dodecahedral or icosahedral symmetry of the smaller, and all of them are actually icosahedrally symmetric. But these shells essentially protect the viral cargo and polymerize spontaneously due to free energy minimization. And the main point of the talk will be how to come up with, once you have the mathematical stuff down for modeling capsid assembly kinetics, which would be a simple ODE model here, differential equation model, you can essentially get the information you need for the assembly kinetics model from a combination of graph theory algorithms overlaid with the face representation of the polygons here. And we'll go through like a toy example of a tetrahedron assembling from triangular subunits. So if you have the left-hand side is just the rate of change as in any differential equation model, and you have essentially cyclic mass flow with the green arrows representing forward mass flow towards the target goal of, in this case, Z sub 4, where the subscript just represents the subunit size. And you essentially have a couple biophysical parameters in addition to standard reaction kinetics that account for the physical scenario that we're in, where in this case you have the Kf, which is the forward reaction rate, the Kb in the right hand, the two right terms of each equation. You have the backwards rate, and those each have their own units, and then they have conceptual units of per binding site. So you can imagine on the triangular subunit, which is x'd out because you can solve for that in terms of the other equations. You can see 3 edges are exposed, and as these things come together, the hydrophobic surface areas are buried on the edges, such that when you have one come together, you have one edge buried, one unit essentially of hydrophobic surface area, and then another subunit comes together. So you sequentially add single triangular subunits to form Z2 from 2Z1, Z3 from a Z2 and a Z1, et cetera. And you essentially just propagate this on to whatever size Zn, Z sub n. And you have to account for, in the forward and backwards reaction rates, you have to account for the difference between what is observed in vitro in experiments. So in scenarios where you're trying to do light scattering curves or something like that with capsid assembly kinetics, say with hepatitis B virus or bovine enterovirus, something like that, you have to account for what you'll see macroscopically, which takes into account the conceptual unit of per binding site and accounts for the number of binding sites that lead to and from a given intermediate. So in a situation where you have a monomer, that's the leftmost figure with the X over it, 2 of those will come together, and there are 3 different positions on which you can bind to give a Z2 from 2Z1. Similarly, there are 2 binding sites that are both equivalent for Z2 to lead to the Z3, et cetera. You just add an additional index if you have multiple intermediates in a given size configuration for a larger structure. So if you have more equations, like say a dodecahedron you're assembling, that would at minimum be 12 equations, because you assume that it adds sequentially and there are 12 faces to a dodecahedron. And you have to account for the forward reaction rate microscopically and macroscopically in terms of what you'll see in experiment, which has to account for things like the number of binding sites that will lead to the next intermediate, because that will scale the reaction rate linearly from the microscopic per binding site reaction rate to the macroscopic observable reaction rate. So if you have dodecahedral assembly, which this model was established just in plain text form, just by doing it all in your head, all of the combinatorics in your head. If you have a simplest case model here, bovine enterovirus and a lot of other viruses, picornavirus, I believe, form dodecahedral shells where the finished product is just a set of pentagons that come together to form a dodecahedron. You can look at the kinetics here. The left is a physicist version with mass fraction. The right is concentration. They're both equivalent. You start with an entire population of monomers. So just in our previous example, it would be just the triangular subunits in solution, and they gradually assemble just following the scheme that was shown to assemble a roughly 85% capsid under these conditions. And with the parameters on the sliders here. And the other biophysical parameter that is incorporated is the third one from the top on the sliders, delta G, which is just the binding free energy. What is the driving force bringing these things together? Typically, again, for hepatitis B virus, that would be hydrophobic surface area burial on the interstitial parts of the subunit. So if we go to the next part, I think I can probably skip I'm used to talking to biologists, so I give an introduction on graph theory, but I think we can probably skip that if I can find my mouse. So yeah, a graph is just right. It's just nodes joined by edges. And graph 3D functionality was actually added while I was working on this problem. I kind of thought of the scheme of using graph theory and the count of the edges to accommodate for the stability of a given intermediate in version 9 before graph 3D was available. And I was very excited when graph 3D was being developed. It was accessible before, but you had to circumvent some errors and stuff like that. So it was exciting that Mathematica 10 came out shortly after that. More very laggy graphics here showing the property of duality, which just shows that you can represent as a subunit, or represent a subunit, as a vertex. And as such, there's an edge in the graph, the overlaid graph on the rightmost figure. Everywhere there's a graphical edge, everywhere that there's a conceptual edge representing hydrophobic surface area burial, such that the assembly process and the intermediates are all rendered computationally tractable. Because if you want to do the combinatorics of a scenario like that, you can type in plain text the equations for, say, the most stable model, which is what I showed on the previous slide, where you have just the most ligated intermediates of, say, size 3 or 4, where instead of, you just don't even account for the possibility of there being linear chains of polygons. You only account for the clustered versions that you see, like, say, just on the top half here for size 6. So essentially, you just represent capsid subunits as the vertices. You represent the subunit contacts as edges, and this renders the entire problem computationally tractable in a way that a computer can handle rather than a human. And the computer thinks about the assembly of the octahedron on the left here in terms of the overlaid blue cubic figure, whereas we think of it in terms of the faces coming together. They're both equivalent, and it's kind of unnecessary to have the face representation, but it's good conceptually to have a figure like that, especially in talks that are very interdisciplinary. So we will talk a little bit about if you want to accommodate for, say, in a scenario where you have kinetic trapping, if you add an appreciable amount of salt that electrostatically screens the fact that the subunits are all identical, so if there's any charge, say positive charge on the hepatitis B virus subunit, they're going to repulse each other. But if you add salt, that electrostatically screens the positive charge, reducing the extent to which they repel, and therefore increasing the extent to which the hydrophobic surface area causes the subunits to want to come together. You can actually get scenarios experimentally where you see such rapid depletion of the subunit pool that as mathematically it's modeled for that reason, you can see experimental scenarios where you get such rapid depletion of the subunit pool that you get large populations of partially finished capsids, but no no fully built houses, essentially. You have a bunch of part-built houses, and then you run out of wood. Is essentially the idea here. And obviously, if you want to account for something that you're going to try to see in experiment, you have to eliminate assumptions where you can. And one of the most glaring assumptions is the assumption that if this is a stability sorted figure, then the most stable, the ones that are the least linear and the most clustered with the most number of edges in the underlying graph are at the top. Then you want to incorporate the other energy minimization pathways that are possible, such as the second or third layer here, which each successive one is of comparable stability or less. So as you incorporate more energy minimization pathways, the dodecahedron happens to have 73 different possible state variables that can go into the model. You get more realistic, and the capsid assembly curves get more and more like the light scattering curves that you see in solution. But this again requires elimination of the assumptions that you make for a simplest case model, which was made in something like 1994, to now where you have an algorithm that is able to render the situation more computationally tractable. So we can look at a more utilitarian view of, again, a graph version of the assembly pathway. So this is the same figure that I was showing before, except with each vertex as an intermediate, and each, or isomorphism if you please, and each tier as a different size. So you can see of Z sub 6, the size 6 isomorphisms, you have something like 20 different intermediates for the dodecahedron. And of course, as you scale up in size, this problem scales combinatorially, which is comparable to exponentially. So as size increases, it's less and less likely that you'll be able to exhaustively enumerate. And if you recall, hepatitis B virus has 120 subunits, so that's an order of magnitude larger a problem. And they've been able to demonstrate with a previous sweeping algorithm that there's something like 2.6 million intermediates that can be enumerated for a size 30 structure. So it's obviously kind of a fool's hope if you don't have a strategy. Essentially, you can kind of conceive of what the effect on the mathematics would be if you account for multiple intermediates. It just changes the four terms. So say we're considering the equation for Z6,5, the fifth intermediate of size 6. Then instead of having one term for the polymerization to that intermediate and the dissociation from the larger intermediate to that intermediate, because we're just considering association and dissociation of one subunit here. So you have an up to component for polymerization to that intermediate. You have dissociation to that intermediate from size Zn plus 1. Here it would be Z7I. And you have negative terms accounting for the change in the rate of change of here Z6,5 due to polymerization of Z6,5 with Z1 to form any of the Z7s. And you have similarly dissociation of Z6,5 to the various Z5 structures. So it just essentially just makes one term per section here into many terms that I'm not going to bother scrolling over since the mouse is being finicky. But you can imagine that if there are 20 intermediates of size 6, there's going to be a lot more mathematical terms accounting for the interactions between any two intermediates than there would be if you just had one intermediate per size. The means by which we actually got this computationally was by means of a Markov chain Monte Carlo, so a memoryless stochastic Monte Carlo experiment, essentially, where we can just say, we'll see if it lags too much here, and if it does, I'll just describe it. You can very quickly make a do loop that constructs from the same, I think I start with vertex 1 each time, which happens to be that bottom face, I guess, and it constructs it here. It's just reconstructing the same trajectory, but if I instead click this and tell it to give me a new trajectory, it goes through a different trajectory. And if we freeze it at any one size, you can say, size 5 here. Essentially what the algorithm will do is you say new intermediate, you have the first one, you put it in an intermediate bank or what you're going to construct the model state space from, and then you generate a new intermediate, compare it using isomorphic GraphQ or a query on whether or not the new intermediate is isomorphic to the one in the bank or any of the ones in the bank sequentially. And if it's not isomorphic and not rotationally equivalent using some group theory algorithms in Mathematica, then you can put it in the bank as a new state variable. If it is isomorphic, then you can throw it out and tally the count of that intermediate if you want to keep track of that. So this gives you a means to generate the previous figure that we were looking at for the 73 intermediates of a size 12 structure. And it also gives you a means to bias the assembly process. So in the do loop essentially here, where you add a single subunit per time, you can bias it towards stability such that if there's one node that's going to add 3 edges upon incorporation rather than a node that's going to add only 1, you bias it with some arbitrary bias to preferentially generate most stable intermediates, such that for a larger problem where you can't possibly exhaustively enumerate a size 120 structure and all the combinatorially possible intermediates, you can preferentially generate most stable intermediates to then use in the model instead, because it has been demonstrated, as I'll show, that that is a reasonable approximation to the kinetics of the exhaustive system. We'll skip the rules here. I kind of mentioned them. It's just group theory plus the isomorphism query. Let's see how we're doing on time here. Okay. So if you incorporate 73 state variables rather than just the 12, you can see that it's very similar trajectory, except there's actually a little bit larger a capsid population at early time frames and a compensatory lower fraction of capsid in the late curve before it reaches a similar equilibrium value. And I have comparing figures in the next slide here. And for fitting a system, it's important that the curve fit, the entire portion of the curve. You don't only want the model to equilibrate to the proper value. You want it to have the right form so that you're getting the dynamics right, at least to what extent you have experimental evidence for a curve. So essentially, early trajectories are corrected by the incorporation of multiple intermediates per size, because you are more adequately representing the energy minimization pathways during the assembly process. We'll go to the next slide here really quickly. So in order to demonstrate, and this will probably be the last thing I talk about here, in order to demonstrate that this is a feasible thing to do, think that this could scale up to size 120 rather than just size 12, as I've been using here. You can see that if you only incorporate the size 12 intermediates here, which is the dashed line for this middle figure, is just the top 12 for the dashed line, and then the colored line is the 73 equation exhaustive system. You can see that you get most of the kinetics from the most stable intermediate model that was made about 20 years ago, except when you enumerate them, when you enumerate the other, 60 state variables, you get a very subtle change, but you get very diminishing returns as you incorporate less stable intermediates. So this figure over here, the dashed line, instead of the colored line, still represents the exhaustive model. The dashed line, if you can see it here, represents a 27 equation system, which is the top 3 tiers here. So instead of just the top layer of the most stable intermediate model, you have a truncated enumerated system where you have 27, or the top 3 tiers here. And you can see that it's almost the same kinetics system exactly. You have very little change, but the amount of system change per state variable added is rapidly diminishing as you go deeper into the assembly funnel, it's been called. So essentially, that demonstrates that for larger structures, and we've tested it out in my boss and his collaborators have tested it out for larger structures with a different algorithm that was not really tractable to someone other than the author, really. They've tested it for size 20 and size 30 intermediates and seen similar results, that you can scale this thing such that even though you can't enumerate or you can't integrate all 2.6 million possible combinatorial combinations of intermediates of size 30, you can still get, say, like a rhombic tetrahedron or a triaconsahedron, I think. Even though you can't integrate that, you can integrate a large enough fraction that you see very rapid diminishing returns in terms of the integration of the system and the change in the end capsid curve. the main goal of a project like this would be to do curve fitting of light scattering curves, for example, because light scatters things proportional to the radius of the thing doing this scattering. So essentially, if you have a large capsid, a large oligomer that is in solution, and you shine a light of a certain frequency on it, the light will be scattered proportional to the radius of the thing that's doing the scattering. And you can construct from this concentration curves and essentially analyze the concentration dynamics of the system. And yeah, this was made possible with Mathematica and the enumeration algorithm that I've shown with the graph theory. And I think we're probably running low on time. Okay. Yeah, so that'll probably be the last thing that I talk about. But my boss came up with most of the mathematics, and we're going to try to adjust the mathematics, but at this point, most of it has been a computational problem that we're finally able to address with graph and graph 3D functionality that's been added in Mathematica. So that is exciting, and I think that'll be the last thing that we talk about. We'll skip the biology stuff here.